Welcome to GATE video section presented by SA Engineering College. I am Angelin Jeba, Assistant Professor, Department of ECE from SA Engineering College. Today the topic for presentation is energy bands in intrinsic and extrinsic semiconductor. So first we'll see about the introduction about semiconductors. So what is semiconductor? Semiconductor is it's a conducting material that lies in between the conductor and insulator. So there are two types of semiconductor. One is intrinsic semiconductor and another one is extrinsic semiconductor. So intrinsic semiconductor is also called as a pure form of semiconductor, since the number of electrons and holes in the semiconductor will be always equal. So based on which the Fermi level, so conduction band is always in the topper end and valence band will be seen at the bottom end. So always the valence band will be filled with electrons, whereas conduction band will be zero at zero Kelvin. So there will be the energy gap between the conduction and the valence band is called as an forbidden energy gap. So here for this intrinsic semiconductor, you have a Fermi level, that is energy band based on the number of electrons present. So the Fermi level will be in the midway between the conduction and the valence band. So now when we increase the temperature, or what happens means the electrons from the valence band will be drifted to the conduction band by applying more temperature. So that process is called thermal excitation. And the next type is extrinsic semiconductor. So extrinsic semiconductor it's one form of intrinsic semiconductor, whereas here in the intrinsic semiconductor, if we basically add a doping means adding impurity to a component. So if we add impurity, then it becomes an impure component, then it will be called as extrinsic semiconductor. So there are of two types. One is N-type semiconductor and another one is P-type semiconductor. So based on the majority of carrier concentration, it can be divided into P-type or N-type semiconductor. So for N-type semiconductor, it's also known as donor level semiconductor. So here the pentavalent component are used for N-type semiconductor. So what are the pentavalent component element? Let's say phosphorus and arsenic are used for N-type semiconductor. So here the majority carrier will be electrons, whereas minority carrier will be holes. So here the next type is another type is P-type semiconductor. It's also known as acceptor level. So here the two type of trivalent atoms that are used are boron and aluminium. So here the majority carrier here will be the holes. So based on the majority carrier concentration, it can be split into either N-type or P-type semiconductor. So now the energy bands in extrinsic semiconductor. So as I said, for N-type material we will be using an pentavalent element by which there will be a free electron in space. So the donor level, that is the Fermi level, will be more closer to the conduction band, since there is a more number of electrons, and also we have a extra free electrons, and the level is more closer to the conduction band. Whereas for P-type semiconductor, there will be a donor, there occurs a hole. So what happens means, so the acceptor level will be more closer to the valence band. So this is the energy level difference of N-type and P-type material. So next we'll see some problems related to the related for grade examination. So first one, the energy band gap of semiconductor material to produce violet and its wavelength is given as 4000 Armstrong. LED is how many electron volt? We have to find it. So we know a formula, that is to calculate the energy is given by E equal to hc divided by lambda. So here h represents the Planck's constant, whereas C represents the velocity of light. So velocity it's a constant value, and it is given by 3 into 10 to the power 8, whereas Planck's constant is given by 6 into 10 to the power minus 34. So whereas the lambda value is given as 400 Armstrong. So we know that one electron volt will be equals to 1.6 into 10 to the power minus 19. It's a Coulomb value. So we have to calculate it for electron volt. For that purpose, we are adding that 1 Coulomb value. So totally we will get, after calculation, we'll get as 3 electron volt as the energy of LED. LED is given as 3 electron volt. And the next one is the longest wavelength that can be observed by silicon, which has the band gap of 1.12 electron volt, is 1.1 micrometer. If the longest wavelength that can be observed by another material is 0.87 micrometer, then the band gap of this material is approximately. So we have to find the band gap of the second material that is involved. So the same formula, whereas we have to find the wavelength. So lambda is taken as, so we know that E equal to hc divided by lambda. So here, so we have to calculate the lambda value. So lambda equal to k divided by Eg. So k refers to the constant value, that is energy band gap. K represent the constant value, whereas Eg represent the energy band gap. So now we are going to calculate the wavelength of the first material. The wavelength of the first material is given by k divided by Eg1. Eg represents the energy band gap. So substituting the values for the first material, the wavelength is given as 1.1 micrometer, and the k value it's a constant value. It has to be found from the first material, and the energy gap is given as 1.12 electron volt, and substituting the values and cross multiplying it, we get a k value as 1.1 into 1.12. So this has to be substituted for the second material. So wavelength of the second material is given by k divided by Eg2. So Eg2 can be calculated with a constant value that is found from the first material. So substituting that, we can find the energy value of the second material, band gap value of the second material. And problem number 3, the electrical conductivity of a semiconductor increases when a radiation of wavelength shorter than 1000 nanometer is indicated on it. The band gap of the semiconductor is. So here, to calculate the conductivity, first we have to write the frequency formula. Frequency is given by C divided by lambda, whereas C refers to the velocity of light. So as I said, the energy formula is given by E equal to hc divided by lambda. So we are going to calculate E from this. So the Planck's constant is 6.6 into 10 to the power minus 34, and C is the velocity of a light, which is given by 3 into 10 to the power 8, and we are going to calculate the lambda value. So lambda is, we have to find the value of lambda. Lambda is given by 1000 nanometer. So substituting that, we'll find the energy value. So energy is approximately given by 1.24,000 divided by lambda, and substituting the lambda value, we can get that E equal to 1.24 electron volt. So now we will go to equilibrium carrier concentration. So equilibrium carrier concentration, it refers to the stable number of electrons and holes that is present in the semiconductor material. So when there is no application of voltage. So so this is mainly concentrated using a law of mass action. So what is law of mass action? Law of mass action is given by Ni square, which is equal to a product of N into P. So N refers to the electron concentration, and P refers to the hole concentration, and Ni refers to the intrinsic concentration. So intrinsic is the semiconductor material, which is a pure form of semiconductor material, which has both the number of electrons and number of holes are equal in state. So now for the material that doped material, that is for extrinsic semiconductor material, that is silicon, the values of N refers to the electron band and P refers to the hole concentration, which is given by NC equal to, NC is the density, NC refers to the density, and exponential of minus of EC minus EF. EC refers to the energy at the conduction band and EF refers to the Fermi level energy, divided by KT. K refers to the Boltzmann constant and T refers to its temperature. Similarly, for hole, it is represented by NV. NV represent the it's the density of a valence band. So exponential of minus. So here it refers to the difference between the Fermi level and the valence energy, divided by Boltzmann constant into the temperature. So this is the formula which is given for the conduction band. The conduction band refers to the number of holes, whereas valence band refers to the number of holes, and conduction band number of electrons. So based on this, the problem will solve a problem. So first problem, the two initial identical samples A and B of pure germanium are doped into donors to concentrates of 1 into 10 to power 20 and 3 into 10 to power 20 respectively. If the whole concentration in A is 3 into 10 to power 12, then the whole concentration is B at the same temperature will be. So here in this question we can understand that they are taking two samples, and in sample 1 both holes and electrons are given, the values are given, whereas in sample B the concentration of the hole is missing. So we have to calculate from the sample A. So first we know the mass action formula, that is given by Ni square equal to N into P. So based on that formula, when we find the product of electrons and holes, we will get Ni square value. So this Ni square, that is intrinsic concentration value, so this can be substituted for sample B to find the value of holes. So see here, so the Ni square is found to be 9 into 10 to power 32. So this value is substituted to find the value of P. So if you write in terms of P, we can write it as Ni square divided by N. So calculating this, we can get 3 into 10 to power 12 is the whole concentration of the material number B or material 2. And the next problem is 1 centimeter cube of pure germanium at 20 degrees centigrade contains 4.2 into 10 to power 22 atoms and 2.5 into 10 to power 13 free electrons and 2.5 into 10 to power 13 holes. 0.0001% of arsenic doping donates an extra 10 to power 17 free electrons in the same volume. The approximate number of holes in 1 centimeter cube in the doped semiconductor under equilibrium condition. So here from the problem itself you can analyze that it is a doped material. So it is an extrinsic semiconductor material. Here they have given that both N and P are equal, and which is given as 2.5 into 10 to power 13. So after doping, initially it is in intrinsic state, so the number of electrons and number of holes are same, and when it is doped with an arsenic material, so they are doping with an arsenic material and it is increased to, the N value has been increased. So this is an N-type semiconductor material. So it is doped and with arsenic, so added summed with 10 to power 17. So now using mass action property, the same formula is applied, which is N into P equal to Ni square. So substituting the values, now the value of N has been changed. So 2.5 into 10 to power 13 plus the doped value is introduced into P, which gives us Ni square. Ni square is given in the question, which is 2.5 into 10 to power 13 the whole square. So substituting those values, by which we can find, and cross multiplying it, we can find the value of P to be 6.25 into 10 to power 19 under equilibrium condition. So this much number of holes will be present in that particular material under equilibrium condition. Okay, thank you. We'll see in the next video.